Welcome to lecture 1 of week 2. Today, we will talk about the concept of a maximum and minimum of a set. Let's start by seeing the definitions. Given a set S of real numbers, if there is an element of S that is greater than all other elements, we say that S has a maximum and denote the maximum element by max of S. Similarly, given the set S, if there is an element that is less than all other elements, we say that S has a minimum and denote it by min of S. Let's talk about some examples. Given the set S containing negative e, negative 1, 0, 2, 3, and pi, the maximum of S is pi, since it is approximately 3.14 and bigger than all other elements. The minimum is negative e, which is around negative 2.8. Note that for our ordering, the minimum is the most negative number and not the one with the smallest absolute value. Now, sets don't always have maxima or minima. Here, let's first look at the sets of rationals, integers, and naturals. None of them have maxima. The first two sets, the rationals and integers, don't have minima either. But the natural numbers has a minimum. Remember that we start counting from 1 in this class. Let's give a proof of the lack of maxima for these sets. The proof is in the spirit of a children's game of name a bigger number. Suppose x is a rational number. The same proof also works if we replace the rationals by the integers or naturals here. Suppose x is a rational number, then x plus 1 is also rational. Since given any number in the set, you can always find another bigger number, this shows that the set cannot contain a biggest element. This is the spirit of how one would generally try to prove that a set lacks a maximum or a minimum, by devising an algorithm that, when given an element in the set, provides another bigger or smaller element. Here, the set S contains the reciprocals of all natural numbers. This set has a maximum equaling 1. It, however, has no minimum. We give a proof of the latter fact. Given an arbitrary element of S, we know it has to be of the form 1 over n for some natural number n, this being the definition of the set S. We then try to find an even smaller number. To do so, we add 1 to n and consider its reciprocal. This number is in S because it is again in the form of 1 over a natural number. Since the denominator is bigger, this means the reciprocal is actually smaller. The following proposition is useful and obvious. We include a proof as a review for proof by induction. Proposition: every non-empty finite set of numbers has a max and a min. This is a very general strategy to prove statements that hold for all non-empty finite sets. Every non-empty finite set has a cardinality that is a natural number. So we will rewrite the statement to one that concerns only sets of exactly n elements, and then run induction on n. Let P of n denote the statement, a set of n elements has a max and a min. We will use induction to prove that P of n is true for every natural n. We first prove the base case, n equals 1. This holds because when your set has only one element, there are no other elements. This means that the element is certainly bigger and smaller than any other element, and hence is both the max and the min. We next prove the induction step. Assume for induction hypothesis that P of n minus 1 is true. We wish to prove that P of n is true. Given an n-element set S, we can divide it into two portions. An n-1 element set A and the leftover element, which we'll call X. The induction hypothesis applies to A, and hence A has both a max and a min. We concentrate on the case for the max. The case for the min is similar and omitted. Since the less than comparison on real numbers is connex, meaning that any two numbers are comparable, we know that either max of a is bigger than x or max of a is less than x. Max of a cannot equal to x since max of a is an element of a and x is not an element of a by design. If max a is bigger, then we see that the max of s is the same as max of a. The element that is the max of a is bigger than any other element of a, and we just saw it is also bigger than x, so it must be bigger than any other element of s. If max a is smaller, then we see that the max of s is x. For by transitivity, since max a is at least as large as any other element of a, we see that x is strictly larger than any element of a. Since a comprises the entirety of other elements of S, this proves that x is larger than any other element of S and is the maximum. A consequence of this proposition is that sets that fail to contain their maxima or minima must be infinite. Let's give one final example for this lecture. Here, S is the set of all rational numbers strictly smaller than 1. I claim it has no maximum. We will give two proofs of this fact. The first proof, we will use the Archimedean property. The second proof, we will work directly with the numbers. Here's the proof using the Archimedean property. First, we take an arbitrary element Q from the set S. By definition, the element is rational. Next, the number 1 is also rational, and 1 is greater than Q since Q is in S. Using one of the consequences of the Archimedean property, which appears as corollary 10 on the usable statements sheet, we can guarantee the existence of a rational number r between Q and 1. This r must be an element of S since it is a rational less than 1, but it is also greater than Q, so Q cannot be the maximum. Since the Q selected originally is arbitrary, there cannot in fact be any maximum element of S, and S has no maximum. In this second proof, we explicitly give a formula for the rational number that is bigger than a given one in S. Start again with Q in S. We use the fact that it is rational to write it as A over B. Since Q is no more than 1, we have that A is less than B. Since A and B are both integers, this means that their difference is at least 1. So if we double everything, we have that twice B is at least twice A plus 2. Or that twice B is strictly bigger than twice A plus 1. So if we divide 2A plus 1 by 2B, we get a rational number that is bigger than Q and less than 1. This number must also belong to the set S, so Q cannot be a maximum of S, and in fact, there can be no maximum of S at all. Notice that the choice of 2A plus 1 over 2B is just one of infinitely many formulas that could work. For instance, another viable choice is to take the average between Q and 1 to get the third rational number. We conclude by asserting the uniqueness of the maximum and minimum of a set. Proposition: a set can have at most one maximum and at most one minimum. We give the proof for the case of the maximum. The other is similar. The structure of this proof is typical of most uniqueness proofs. To prove that there is a unique element satisfying a certain condition, frequently we posit that P and Q are both elements that satisfy the condition, and try to prove that necessarily P and Q are equal. So, as a first step, we posit that P and Q are both maximum of S. Notice that in this step, we did not assume that P and Q are distinct. Since they are both maxima, they must be greater than or equal to each other. So, by the antisymmetry of the less than or equal to relation, P must equal Q. And this concludes our proof. Okay, this ends the lecture. See you next time.